Swayam Prabha. Digital India. Educated India.
Okay, welcome to the 31st lecture in mechanics of materials. We were looking in the last class on inflation of an annulus cylinder. Basically, we used it as an example of how to formulate a boundary problem systematically using theory of elasticity. That is, we assume a displacement field. From the displacement field, we computed what is the strain. From the strain, we computed the stress using the 3-dimensional constellation, and then we found the unknown component, the displacement field, from the equilibrium equation, that is divergence of sigma equal to 0, assuming there is negligible body forces and the body is in static equilibrium. The equilibrium equations boil down to requiring divergence of sigma to be equal to 0. Okay. Using that, we found that the displacement field u of r has to be given by C1 r by 2 plus C2 by r, and then we found the constant C1 and C2 such that for the boundary conditions for the given problem are satisfied. In particular, in this problem we had pressure applied at the inner surface and no pressure applied at the outer surface. So, that was sigma rr at Ri, the inner surface, must be equal to minus Pi, the applied pressure at the inner surface, and sigma rr at R naught must be equal to 0, the applied pressure at the outer surface. From that condition, we found what C1 and C2 are. Okay, and then we estimated the stresses again, going back to computing the strain, and from the strain plugging it in the constellation to compute the stresses as given here. Okay. And we rationalize that the predominant stress that is produced in this boundary value problem is the OOP stress or sigma theta theta stress, which is approximately 10 to 20 times more than the radial stress. Okay. Radial stress is sigma rr and it has a variation as shown here. It varies from minus Pi at the inner surface to 0 at the outer surface, the boundary condition that was specified, and whereas sigma theta theta is a tensile stress which varies from a maximum value at the inner surface to a minimum value at the outer surface, which is roughly 2 times Pi Ri square by R naught square minus Ri square. Okay. And then we can go back and compute what the strains are also from the expression that sigma epsilon rr is dou u r by dou r, which is C1 by 2 minus C2 by r square, and from the fact that epsilon theta theta is nothing but u r by r, that is C1 by 2 plus C2 by r square. Okay. From these expressions you can compute the strains also, because you know what u of r is. Okay. Now, we will proceed further and see what happens when the boundary condition changes and what are the various variations in this problem that we can study. Okay. The first thing is, say I pressurize it both from inside and outside. I am not going to solve this entire problem, but just indicate how to go about solving this problem. Okay. Is pressurized from outside by a pressure P E say. Now, this pressure is again opposite to the outward drawn normal to that surface. So, this is the negative pressure. So, the boundary conditions now will be sigma rr at r equal to Ri is equal to minus Pi, same as what we saw in the last class, last lecture, and sigma rr at r equal to R naught, instead of being 0 now is going to be minus P external. Okay. The externally applied pressure, negative because it is opposite to the direction of the outward drawn normal. The stresses which are parallel to the outward drawn normal are always positive. Stresses which are opposite, the forces which are acting opposite to the outward drawn normal are negative stresses. Okay. So, you got these two expressions now. So, your evaluation of the constant C1 and C2 will be different for this case. It will involve Pi and Pe, and you can go about doing the same thing, plug it into the constellation, find the strain, plug it into the constellation and find the stresses. Okay. And now let us say instead of cylinder which is armless cylinder, I have a solid cylinder pressurized from outside, then what will happen? Say I have a solid cylinder pressurized from outside. This outward acting pressure would be normal to the surface. Okay. So, this PE is acting in a solid cylinder with x and y oriented like that. Now, what are the boundary conditions you have? You have only presumably one boundary condition, right. You have sigma RR at R equal to R naught to be given by minus PE. Okay. What is the other boundary condition that you will use? The other boundary condition comes from the fact that the displacement field should be bounded in the domain of the problem. Okay. We got u of r to be C1 r by 2 plus C2 by r. Okay. As r tends to 0, you find that C2 by r goes to infinity, which means the center of the cylinder has a infinite displacement, if this were to be the displacement field, which is not allowable. Okay. And hence you set C2 to be 0, C2 is 0 for a solid cylinder, since displacement has to be finite in the domain of the problem. Okay. So, that is the second boundary condition that you have. Now, you have only one constant which you can find from the condition that sigma RR at R naught is minus PE. Okay. Now, I can have another boundary condition wherein the inner surface can be held fixed. Say I have a rigid body, a rigid steel rod put into a rubber pipe, and I am pressurizing this pipe from outside, and I am pressurizing this pipe from an outside pressure, say. From outside pressure PE. What is the boundary condition now? Still let me have my axis as x and y here. Still my boundary conditions would be sigma RR at R equal to R naught, the outer surface is minus PE, where this is R naught and this is Ri. Now, what is the second boundary condition that you will have? The second boundary condition is, since the inner surface is resting against a rigid body, this surface defined by R equal to this inner surface will not get radially displaced, since it is resting against a rigid body. Okay. So, the boundary condition would be u of r at r equal to Ri has to be equal to 0. Okay. So, this is the second boundary condition that we will use to solve this problem. Okay. Now, I can, after setting this to be 0 and using this boundary condition, I can look at the problem wherein I can look at R naught by Ri tending to infinity, meaning I have a infinite domain, the center of which is a rigid body. Okay. So, in that case, if I apply an eq biaxial pressure, that is the idealization that you get from solving this problem in the limit R naught by Ri tending to infinity. Okay. So, this will be this boundary conditions plus this condition gives us the solution for infinite domain with a rigid inclusion subjected to equal biaxial state of stress. Okay. Similarly, I can have a case wherein the external pressure alone, similarly I can have a case of an external pressure alone applied in this domain PE, an external pressure alone applied in this domain, wherein now the boundary conditions is obvious, should be sigma RR at R equal to Ri has to be equal to 0 and sigma RR at R equal to R naught would be minus PE, and for this boundary condition plus the limit R naught by Ri tending to infinity, you will have an infinite domain with a circular hole in the middle subjected to an equiaxial state of stress. Okay. This solution will correspond to an infinite domain with a circular void subjected to equal biaxial state of stress. Okay. This infinite domain means basically you have some domain like this which is extending towards infinity both in x and y direction, and you have a void, a small void, in other words located at the center of the coordinate system. Okay. So, this azimuth shape of the domain means it is infinite, it is extending to a large area, okay, and you are subjecting it to equiaxial pressure PE in all directions. Since the domain is infinite, the PE will become normal to the surface, it is always normal to the surface, so it will become equiaxial state of stress. Okay. So, basically it is not now in all this we had the basic displacement field as u is a function of u of r ER, but this also can change. I can superpose axial deformations which will be plus epsilon z times z E z, which is the axial expansion or contraction, the axial displacement is given by epsilon z times z. Okay. I can superpose the torsional displacement which in this case would be given by omega z E theta, okay, omega z E theta, which I can superpose in this also, which will be the angular displacement, and still for this displacement field also u of r by r would be C1 r by 2 plus C2 by r, because these displacement are orthogonal to the radial displacement and the superposition is allowed, which means this is a small deformation linear constellation that we are studying, hence you can superpose solutions. So, you can study solutions which have only this component or which has only this component or one which has only the torsional displacement component, okay, which has the torsional displacement component, or I can study only this torsional rotation component. Okay. In each of these cases you have to rederive from the first principles, find the strain, use the constellation to find the stress, use the equilibrium equations to find the unknown components of the displacement field, and then you go back, plug that in into the strain field and find the stress again, and that will be your solution for the problem. Okay.